is, okay, got it, is that there is improvement, that the number of tools that you can use increases. They may not yet be as user-friendly as those for ordinary differential equation, but still there is progress. And so I'm optimistic that in the long run, we can actually get in a situation where there are good and tested and easy to use tools. Now, when I want to promote renewal equations, I'm a very good company, because that's actually what Kermack and McKendrick did in 1927. And they were, I think, stimulated by Ross, the Ronald Ross, who found that malaria was transmitted by mosquitoes and made many models. He too has promoted this, I think, and has stimulated McKendrick to do this. So I want to tell you about this Kermack-McKendrick model from 1927, not the way it is quoted in most papers that you read, that you see that are published, but the way it really is. And let me first remind you of the setting for this paper. It's considering an outbreak of an infectious disease. An outbreak means in particular that demographic turnover, so the inflow of new susceptible individuals by birth, is not taken into account. Also, a loss of immunity due to the disease itself is not taken into account. So once you have had the disease, that's it. It will never get back to you. And finally, there is the assumption that everybody is equally susceptible. And later in the talk, I will gradually discuss each of these three assumptions and then tell you how one can also formulate renewal equations when they don't hold. But for now, this is the assumptions. And then this is the Kermack-McKendrick model. Two equations, no more, just two equations. And they are actually, in some sense, trivial, because they are just a matter of definition. First of all, if you define the force of infection, this capital F in the picture, as the probability per unit of time for a susceptible to get infected, then when everybody's equally susceptible, it's immediate that the size of the susceptible subpopulation decreases according to this differential equation. And here, the product of F and S is called the incidence. It's the number of new cases per unit of time. And note, please, that you can either write the incidence as F times S or as minus the time derivative of S. And that's because the susceptible population is not changing in any other way than by just people getting infected. And I will use both of these ways of writing the incidence later on. And then the question, of course, is what is this force of infection? Well, also the second equation is a triviality because of the definition of A of tau. A of tau is the expected contribution to the force of infection by an individual that was infected time tau ago. So after time tau, after becoming infected, this is how you contribute to the force of infection. So in other words, when you get infected, a clock starts, and when this clock has time tau, this is how you contribute. And then it's just like in mass action, you accumulate the contributions of all the individuals being infected time tau ago, and you have this relationship. Now, expected refers, of course, to a stochastic process, but I'm not defining what it is. And that's because I want to keep it completely general. Later on, we will get some examples, but the idea is just whatever stochastic process you might want to consider, you can still specify that later. So this is very much a top-down approach where you start general and abstract, and then later on maybe fill in details of how to get to concretely computable A of tau. But in any case, the A of tau combines two types of information. One is the infectiousness of an individual, so resulting, of course, from a vis-in-host process in which the infectious agent and the immune system are combating each other. And then it's like the total amount of infectious material that you shed after a certain time tau or are expected to shed. But the other important factor in this A of tau is the contact process. So it's also describing some aspects of this contact process. Now let's analyze this couple of two equations. And first of all, let's notice that when S is identically when S is identically equal to the population size capital N, then we have a steady state. Then there is F is 0, or maybe I should put it this way, where F is 0 is a steady state. And then you can put S equal to the total population size N. And linearizing around this steady state, which is what mathematicians do, amounts simply to, biologically speaking, ignoring that the susceptible population is going down because the disease makes victims. So you simply keep the S at the level N that it has in the very beginning. And then you get a linear renewal equation, which is actually identical in form to the equation that Lotka considered when he made models for age-distributed populations, in particular human populations. It's exactly the same equation, but with different notation, different symbols, but mathematically speaking, it's exactly the same equation. And the key point is that this equation is linear as well as translation invariant. And whenever you have an equation that has these two properties, you always should try solutions of the form e to the lambda t. Basically, because for exponential functions, you have the translation amounts to multiplication by a constant. So if you try that, you find that in order for this indeed to be a solution, the lambda should satisfy a certain equation. And that's the so-called Euler-Lotka or characteristic equation, named after Euler and Lotka. But one should also note that when we talk about renewal equations, it was actually Feller that developed a lot of theory, also motivated by Lotka's work. And in particular, if you look in the second volume of the treatise on probability theory by Feller, you find a lot of information about renewal equations. So I want to emphasize that Feller was really a pioneer in this field. Now, when we have this characteristic equation and we realize that A of tau is positive, is non-negative, it's clear that if you look for a real solution for lambda, there can be only one. And this real root exists indeed under very minor conditions on the function A of tau. And we call it the Malthusian parameter. And I like to note here that the shape of A matters. Now, what do I mean by shape? It's of course a bit vague terminology, but I mean things like shifting the A. If you shift it in time, say to the right, you will have that the contribution to the force of infection will be made later, and that has an impact on this Malthusian parameter. So the form and where it is positioned on the tau axis, the mass of A of tau, that kind of things I collectively call the shape of A. Now, in contrast, if you look at the basic reproduction number R0, which is defined here, and which amounts, if you consider the interpretation of these things, to the expected number of secondary cases per primary case in the initial phase of the outbreak, when you can still ignore that the S is going down due to the disease itself, so where it has still the value N all the time, this R0 only depends on the integral of A of tau. So not on where on the tau axis the mass of A is located. And this R0 is the value of this right-hand side of the Euler-Lotka equation as a function of lambda when you consider lambda as a real variable. And then it's the value in 0. And so if R0 is bigger than 1, you have a real root that is bigger than 0. And there is a real root because this integral at the right-hand side of the Euler-Lotka equation goes to 0 when lambda gets large, when it's real. And so we see that the sign of R0 minus 1 is the same as the sign of R. And so we are, in that sense, relieved that when you look at population or look at the increase of the infectious agent, either in terms of generations, which is what R0 does, or in terms of the real-time growth rate, then you always find that if you have growth in one way of looking, you have it in the other as well. Now, another thing to remark here is that I noted already that R, little r, the Malthusian parameter, is influenced by the shape of A, whereas R naught is not. And this is important if you look at data in the initial phase of a new disease somewhere, then you can try to determine the R from data, the little r, the Malthusian parameter. And from this, you want to estimate R naught, because R naught plays a big role in control effort that is needed to maybe get the disease controlled such that it will disappear again. And to get this information from observations about little r to the R naught, you need information about the shape of the A of tau. That's an important point. Now let's see if you do the nonlinear case, where you do take into account that S decreases when the disease, when the epidemic progresses. Then I want to replace the incidence term not by F times S, but by this minus the time derivative of S. And then you can integrate this identity with respect to the t variable, say from minus infinity to t. And then at the right-hand side, you can interchange the two integrals, and you can evaluate the time integral, and you get this identity that is written here. On the other hand, if you integrate this, ds dt is minus fs, you find that s of t is n times e to the power minus this integral of f. So this cumulative force of infection is this integral. And so if you combine these two identities and write little s of t as the proportion, as the ratio of s of t, capital S of t, with the total population size, so the fraction of individuals that is susceptible at time t is the little s of t, you get one scalar renewal equation, but now a nonlinear one for the variable little s of t. And so this is really the Kermack-McKendrick renewal equation model in its full nonlinear form. And for those of you who like dynamical systems, I like to stress that you should look at this equation as a delay equation, by which I mean a rule for extending a function of time towards the future if you assume that the past is known, so you can treat that as known. To get started, you have to make this assumption that it's known. Later on, you extend the function on the basis of the rule, and so everything you constructively define is actually known. And if you extend this function and shift along it, then you get a dynamical system, just because the shifting along a known function defines a dynamical system. And that's the way to think about this as a dynamical system. But that's not the point of this lecture. I want to focus on renewal equations in the context of epidemic models. Now, to find the final size of the equation is simple, because you can look at the probability to escape from the whole outbreak, which is this little s at infinity. And then if you take just the limit time tending to infinity in this nonlinear equation, using the integrability of A of tau, which has to be an assumption, but it's a minor assumption, you get this final size equation, which has a probabilistic interpretation, because both at the left-hand side and at the right-hand side, you have the probability to escape the infection during the outbreak. In the left-hand side, directly by the definition of little s, and the right-hand side as e to the power minus the total force of infection that has been experienced by the individuals that escaped. And so here again, the final size only depends on R naught, and so only on the shape and not on the form of the A of tau. Sorry, I say the wrong way. The shape of A is irrelevant for the final size. So the form of A is irrelevant. And this is a bad drawing of how actually the fraction that falls victim to the disease depends on the R naught. The point is just that it's a steeply increasing curve. So already for R naught not so very big, it's a substantial fraction that falls victim to the disease. That's the main point. Okay, so this is the general Kermack-McKendrick models. Yet I would say that 99,999 of all models for epidemics are compartmental models, if you look in the published literature. And how do these fit into this renewal equation business? Well, that's very simple. Whenever A has a specific form, it's a matrix exponential sandwiched between two factors. So you have a factor U that you should consider like a linear functional on the factors, and V as an initial factor in the space of factors. And then we have a dynamically varying e to the tau sigma that acts on this factor V. That's how it fits in, because if you have this situation, you can reduce it to a ordinary differential equation system. And let me explain how this works for the special case where we have the SEIR compartmental model. I assume that the audience is very familiar with this. And so I take this example. So first of all, S dot is minus Fs, as I already had in the very beginning for the renewal equation formulation. And then we have two more variables, E and I. And by themselves, they have a dynamics, and that's generated by this matrix capital sigma, which means just that the sojourn time in the E state is exponentially distributed with parameter little gamma, and the sojourn time in the I state is exponentially distributed with parameter alpha. And if you move out of the E state, you move into the I state. So that's all what the sigma says. And then the phi tells you how you enter this EI subsystem when you get infected. And that's with the state capital E. So therefore the V is the factor 1, 0. And then there is a magnitude for this factor, and that's the product of S times S. So that's the incidence at time T. And how is F related to this EI factor? It's just let the functional U act on the factor EI. And in this case, only when you are in I, you are infectious with contribution to the force of infection beta per capita rate, beta. So that's why it has this form 0 beta. And in general, you have just an X variable rather than an EI, and it may have system size 27 if you have complicated ODE models where you have like people that are not giving any signs of having the disease, and others that that actually show symptoms. So you have different classifications of individuals. You have maybe people in the hospital, people that know they are infected. So you have lots and lots of distinctions. Still, as long as you have just one state at the moment of becoming infectious, which is this capital V, you have a system of equations with, and you have a scalar renewal equation, even though you have a high dimensional, probably high dimensional system of ODE. And this V should be interpreted in general as a probability factor. So if you have asymptomatic and symptomatic individuals right from the very beginning when they get infected, if you make this distinction, then as long as they arise in fixed proportions, you have a single V. If you have this in a more complicated way, then you might need a system of renewal equations. And even then you can work with this U, V and sigma version, but the U and V should have more components. So that's the general theory. And let me also add that if you want to learn more about how this works for delay equations and delay differential equations in particular also, there is a paper by Hans Metz, Mats Gielenberg, and myself in which this is explained. Now, people are used to the linearized system in the form dx dt is sigma plus a matrix T, where T corresponds to the transmissions and sigma is, as I indicated already, taking care of the transitions. And in this case here, the key point is that the T has this form that it is in factor n, which is the total population size, and then these factors V and U is, like I said, a linear functional. So U acts on X to give a size of the vector n times Ux, and V just spans the range. And in particular, T has one-dimensional range, and that's why the next generation operator, which in this setting in general is minus T sigma to the power -1, that you have explicit expressions for the R0 and a scalar equation for the Malthusian parameter, and not that it's trivial from the linear algebra point of view. Okay, so why do all these people use compartmental models, even though this renewal equation catches all of them at once? I think, but I may not be complete in this list, but I think there are three reasons. One is that if everybody does it, you want to do it as well. You don't want to do, many people don't want to be different from other people. So if almost all models in epidemiology are compartmental models, then it takes some courage to write down something that is not a compartmental model. Then, of course, renewal equations are suddenly, compared to ordinary differential equations, unfamiliar. And many people may never have heard of it. So then you don't get the idea. And finally, even if you get the idea, you may be frightened because you think, oh my goodness, but then I have this equation and what can I do with it? I don't know how to handle this, and I don't see any tools that I can use. Now, I think there is optimism here, and one thing is related to discrete time formulations. And let me tell you that my way into discrete time started because somewhere in March 2020, I was approached by Matthias Kreck, a former director of the Research Institute in Oberwolfach, who, triggered by the COVID situation in Germany, wanted to study the data with models, mathematical models. And he wanted to use discrete time models because he wanted to use the discrete time data in the form of, say, day-by-day incidence data for Germany. So he was eager to use a discrete time model. And I, on the other hand, wanted to sell him Kermack-McKendrick, the general renewal equation model. So I started to look in the literature for discrete time versions of the Kermack-McKendrick, the general Kermack-McKendrick model, and couldn't find one. So then I sat down and formulated one myself, and later, together with co-authors Hans Ottmer, Martin Bootsma, and Bob Planquet, we published a paper explaining mainly that extending it or reformulating it in discrete time is kind of trivial, but we like to emphasize that you should not do it as many people that start from ODEs and then write down discrete time variants do, something like Euler forward, or not think in an additive way, but rather in a multiplicative way. So the little s at t+1 should be a reduction of the s of t by a multiplicative factor, which is just the escape probability from the force of infection in this interval from t to t+1, which is what this f hat of t is. So it's now a force of infection over, so cumulative over a time interval. And you get it the same way as before by adding contributions of individuals that were, let's talk in days, if the time unit is days, that were infected at days prior to the present day. So how far back is monitored now by this index K. And then if you escape if it's probability e to the minus f hat, then you fall victim with the complementary probability 1 minus e to the minus f hat. And so what you see at the right-hand side is a of k times the incidence k days ago. So it has exactly the same interpretation as in the continuous time case. And using this discrete time framework, we could actually check that the shape of A, this form of A, this positioning of the mass of A on the time axis also matters for when you will have a peak in the incidence. And that was quite a hot topic in the COVID period, of course, when people wanted to know how soon will we reach the top level, how soon will things start to decline. And also there, you can, but now numerically, using the discrete time formulation, you can find that the shape of A matters. And I refer to this paper of ours for the details. And related to this question of when will things be over? When will we be able to go into the better situation? Let me introduce now here this herd immunity threshold, which is essentially the level of the capital S variable such that you are exactly in the critical situation that the corresponding R naught is equal to 1. So where you switch from supercritical, where it's bigger than 1, to subcritical, where it's less than 1. And it's straightforward in this setting where everybody is equally susceptible to see that the S wiggle is n divided by R naught. So you should multiply by 1 over R naught. So the fraction should be 1 over R naught times the total population size when things are critical. And that's exactly, that's called this 1 over R naught is called this n over R naught is called the herd immunity threshold. And it's exactly the same for when you do vaccination as when the disease itself progresses. But this is peculiar for the case where everybody's equally susceptible. And we shall soon see that the situation is quite different if we have heterogeneity. So let's now introduce, so in some sense, relieve this third assumption that I mentioned about the outbreak situation, that everybody is equally susceptible. So let's assume that there is difference in susceptibility, and that we call heterogeneity. And I'm now mentioning some work that we do together with Hisashi Naba, Martin Bootsma, and Danny Chan, and which is in progress. And here we consider a static trait, so a trait that doesn't change during the life of an individual, that takes values in some set omega, which is a measurable space. And then we have, by arguing exactly as we did before, this now some kind of like infinite dimensional renewal equation, because there's an additional variable x, which is the trait value. But the interpretation is just the same. The A is now a function of 3 variables, not of just tau. And the psi refers to the state of the individual that was infected tau units of time ago. So the tau and the psi refer to the individual that is infectious, whereas the X refers to the individual on which we look for the force of infection. So the one that should escape or get a victim of this force of infection. And the interpretation is exactly the same, but we now have an additional ingredient, which is a measure, this capital phi, which describes the trait distribution. So the integral of capital phi is the capital N, the total population size, but the distribution with respect to the trait is also described by this phi. And the great advantage of this measure is that you capture in one go now the discrete situation where omega is a discrete space and you have just maybe finitely many traits or types or whatever you want to call them, and the continuous situation where X may be described by a continuum variable and phi may be like an absolutely continuous measure. So this is all captured in one go. And you can do theory for this situation. You can look at the Euler-Lotka problem where the equation, if you want to call it the equation, is just that the spectral radius of some operator should be 1. And the operator is given here. Again, you integrate with respect to the tau variable over the whole tau axis with a weight e to the minus lambda tau. But then you act on it with you see it as an integral operator acting on function psi, which are functions of the trait. And in particular, when we put lambda equal to 0, we have the next generation operator, which is also an integral operator, and we call it spectral radius, the basic reproduction number R naught. Now, I will not go into this theory, I refer to the book by Hisashi Naba, but also to recent papers, especially the last paper by Eugenia Franco, who is about to get her PhD in Helsinki with Mats Schielenberg. And I hope you can find it. And if not, send me a message and I will send you her paper. Let me mention, which I like very much, that you can write down the final size equation, which is in some sense exactly the same as it was when we didn't have this heterogeneity. But the only thing you have to do is replace the multiplication by R naught by the action of the next generation operator. And then you have the same equation. Now, I said theory, things get a lot more, say, workable, more that you can do things with it when you are willing to assume that this function of three variables is actually the product of a function of, and especially if you take this last line, when it's the product of three functions of one variable. And it's not unreasonable to assume that. So we assume here that, first of all, the two people that meet in a situation, that have contact in a situation where transmission can occur, have independent, their trait, their properties have independent influence on the likelihood of such an encounter. And then regarding this infectious individual, we assume that its trait and the time elapsed since it became infected have independent influence on this likelihood of contributing to the force of infection. And in that case, first of all, you find that the proportion of individuals of trait X that are susceptible at time t has a specific form. It is e to the minus and then the product of a function of X and a function of time t. It's a function W of time t. And this W is the time component of the cumulative force of infection. The cumulative force of infection is trait specific, but the dependence factorizes as a product of a function of X, A of X, and W of t. And W of t satisfies a scalar renewal equation. And so you take these three ingredients, the C, the A, and the capital phi of the model, and build one nonlinear function, capital phi of W from it in the way as indicated here. And that's the nonlinearity in this nonlinear renewal equation. And in this way, it is written in the book by Hans Heesterbeek and Tom Britton and myself, but it was really used a lot in work by Nigel Goldenfeld in really very nice work that he did at the University of Illinois in Urbana-Champaign, where they very early on in the COVID situation, the COVID outbreak, formed a very multidisciplinary team with all kinds of experts and did a lot of effort to keep the university open, and they managed. And so it's really a paper that I recommend very well. And he used this in a very practical way. And I was very happy, of course, to observe that he used the full Kermack-McKendrick model rather than a compartmental model. And he also, in the following, Gabriela Gomez, and also in a similar way, Frank Jüliger and his group did this. They looked at the herd immunity threshold in this situation where you have a heterogeneity. And the key point is that if you have this separability assumption, you can write the threshold condition that something should be equal to 1 as an equation for the variable W. And if you solve that for the W, you find that the fraction that is still susceptible at this time is this integral of the distribution phi with respect, and then this e to the minus ax times W bar. And so you can compute this fraction. And this has been elaborated in particular in the situation where for a of x, we take x. Now that is just a matter of definition, really, what you take for what you call the trait. So that's hardly lost for any generality. Also, by scaling of x, you may assume that the mean of x is equal to 1. That's just a straightforward scaling of a. And remember that the capital A is a product of various factors, and scaling factors can also easily put into the other, so in the B and the C. So that's not any loss of generality. And then things become very explicit if for this capital phi, this distribution of the trait, you take the gamma distribution. And if you scale the gamma distribution, the mean is 1, you have just one parameter left, and that's usually called P, and the variance is then 1 over P. And already in the period when we dealt with HIV, the beginning days of AIDS, so the 80s of the last century, people, especially also May and Anderson and Dietz, emphasized that if we have the situation that C of psi is psi, that then the R naught is very much influenced by this P. So their main message was, if you look at R naught and have things like sexual activity level among an homosexual subpopulation, don't look just at the mean, but also take the variance into account, because we have this double aspect of activity in both making you more susceptible and making you more infectious once you are infected. And so that's what causes this rise. If we have a high variance or low value of P, then the R naught is very much influenced by that. The R naught is not so much influenced when C of psi is equal to 1. So when the trait doesn't have any impact on the infectiousness. However, Gabriela Gomez emphasized that it has an impact on this herd immunity threshold, as you can see in the right column of this scheme. And that is, of course, because when we vaccinate, we might sample individuals just according to how often they occur in the population. But the disease samples according to the A variable, so to psi itself, or X itself, I should say. And so therefore, in some sense, the disease itself is much more efficient in vaccinating individuals to reduce to get nearer to the threshold, and that you see in the right-hand side. So also when C of psi is 1, the herd immunity threshold is not R naught, 1 over R naught, but it's modified by this variance, and that's an important message. Now, another thing I want to observe here is that once you have this renewal equation for the W, you can actually, in exactly the same manner as I explained before, get ordinary differential equations by assuming that is now the little b of tau is of this form, a matrix exponential sandwich between two vectors. And then you get an ordinary differential equation that you might not so easily derive directly from first principles. Although it has been done, in particular in the work of Frank Jüliger, that is this reference 6 here, for the special case where you have the SIR model, so where the B of tau is beta times e to the minus alpha tau. It is somewhat hidden in his paper, but if you look carefully, you see that this scalar equation for W is there. And you may wonder why it's a scalar equation, why not a system of two equations? Well, that's because this equation really describes the dynamics on the unstable manifolds from the disease-free steady state. And similarly, if you are in the SEIR situation, you get the system of two equations that are at the lower side of this slide. And this is two equations and not three, because we again are on the unstable manifold from the disease-free state. Now, this last equation I haven't seen anywhere in the literature, and I think it's not so straightforward to get the idea to derive it. Once you know that it should hold, it's easy to work towards it, but to get the idea is not so straightforward. I want to mention as a side remark here that Novozilov in already a long time ago, he emphasized very much that with this gamma distribution for heterogeneity, you can get power laws. And he again mainly focused on the situation where C of psi equal to 1 and derived a system of equation at the right-hand side, showing that you might interpret such a power of the little s variable as due to heterogeneity. Now, if you take C of psi equal to psi, you can get this last equation for di dt, which then, of course, is difficult to interpret. And I don't think it's such a useful equation. I think this system here at the bottom of this slide is much simpler. And please note, I want to emphasize this, that you can, with this simple system of two ODEs, you can very easily experiment with this capital psi. So you can do all kinds of distributions, capital phi, all kinds of A and psi, and calculate the capital psi, and then do numerics and find out how this has an impact on dynamics. So I think this is actually a very cheap way of studying the effect of heterogeneity. But for now, let me just conclude this heterogeneity subject by saying that it has an impact on dynamics, this heterogeneity. And if you're willing to make this separable mixing assumption, it's not so difficult to analyze it. Now let's look at non-permanent immunity. And here is an example of a system where we assume that after fixed time tau bar, total susceptibility sets in again. So in that case, the incidence is the product of an F and an S. The S is n minus everything that is on this conveyor belt. So that is n minus the integral over the incidence in the last interval of length tau bar. And the force of infection is the cumulative force of infection of those infected tau units of time ago, exactly as we had before. So you have this renewal equation and nonlinear renewal equation with a scalar one. And you may wonder, how should you analyze this kind of equations? Well, first of all, I want to emphasize again that it's easy to build a discrete time version in exactly the same way as I did for the outbreak situation. So I think if you want to really do like compute orbits, I recommend this discrete time version. The alternative is to look at it as an abstract ordinary differential equation and do pseudospectral approximation. Now, for this audience, I don't have to explain this because Rosanna Familio a couple of weeks ago gave an exposition on this topic. And so I would simply refer to her seminar and show you here just a bifurcation picture where you see a Hopf bifurcation occurring, and it was computed by Francesca Scaravelle with this pseudospectral approximation for this renewal equation that I showed. And the conclusion of this kind of work is that you can easily get oscillations because we have negative feedback, but with a delay, and then you get oscillations. Then there was this other assumption that there was no demographic turnover in the model. If you want to relieve that, if you want to include demographic turnover, and in particular, if you want to work with a survival probability that is not an exponential, and I think there's every reason to do that, because I think far too many epidemic models that include demographic turnover make the ridiculous assumption that people live for an exponentially distributed amount of time. Meanwhile, I've got the age where you wish this were true, but I'm sure in my audience, there are lots of young people who are very happy that this is not true at all. The survival probability for young people is much, much higher for any interval of time than for old people. So a constant survival probability up till about 70, 80, 90 years is much more realistic for civilized, for developed countries than this this exponential. So if you want to include that, then you have to take the age of individuals into account. because that tells you how long they are already living, and so what are their prospects for living any longer. And in that case, you can write the S as a function of both time and age, HA, as the population level birth rate, capital B, times the survival from the death process, times the survival from the infection process, which is just the integral of the force of infection during the time interval that you lived. And if you have time, if you have HA at time t, you were born at time t minus a, and now the time is t. So that's this integral. And then for the f of t, you make again this cumulative version where you add contributions by individuals that were infected tau ago, but they may now also differ in ages. So it's a little bit complicated, but the upshot is that you get a scalar renewal equation for the f of t. So at the level of the renewal equation, it still is a scalar equation, even though it is a little bit more complicated one. And you can do this kind of numerical bifurcation analysis with pseudospectral approximation, just as in the other case. Finally, I want to make propaganda for a work by Kai-Yin Leung on networks, also in this case, but I skip it. It is just a teaser to get you curious, and so I hope you take a look at this paper, which is about also renewal equations, and in particular in the case where, and I emphasize this, to work with networks, you need to have a statistical structure in the network that allows you to average, and this is what these configuration networks allow you to do. And so I refer to that. So let me summarize what is my, my main point. This is that renewal equations are the ideal tool to formulate epidemic models. That's my opinion, and I hope my talk today helps a little bit to convince you that this is true. And then also my optimism is that tools are beginning to become available to analyze these renewal equations. And I want to finish with a request to you. And the request is, next time when you formulate an epidemic, please try renewal equations. Thank you for your attention.
Thank you, Odo, very much for your quite clear exposition. Very nice and interesting. So if there are questions or comments, please ask or use the chat, whatever.
Well, since nobody talks, can I just ask a very minor point? In the fact, I see that you always have a sort of, let's say, bilinear function for getting infected. So you have this term n that comes everywhere in the formula for R naught. I got convinced that somehow the frequency dependent is a more natural formulation, so you don't get all this n. I think that might be easier also as a formulation. What do you think?
Oh, I fully agree with you. It's just that here I assume throughout that the total population is constant. There's no change at all. So in a population of constant size, it's just a matter of how you call the parameters. You can easily scale between one and the other formulation, and it's just the same. So it is a matter of how you write things down. But as soon as you get to a situation where the population size is variable, or when you want to compare populations with different sizes, you have to be very, very careful what you really mean by size. Is it density or is it really numbers? You have to think about how you scale these things. And in this paper that we have in preparation with Hisashi Naba and Martin Bootsma and Danny Chan, we want to also work on that and comment on that. And so I fully agree with you. It's just that here I try to keep it as simple as possible, and then I did it this way.
Okay, thank you. I think Francesca is going to ask something.
Yes, I would have a question. Thank you, Odo. It's always very interesting. And I have a very confused question on something you have only briefly touched upon, which is the case when heterogeneity is not, so the kernel is not separable. Because I was recently thinking so if I consider that the heterogeneity is actually in susceptibility, for example, and then you may have so I was wondering if a non-separable kernel may kind of tackle the problem of those response, like if someone has a higher infectivity and encounters an individual with a lower or higher susceptibility, the transmission may depend on both, on the level of susceptibility and on the level of infectiousness. And so I don't really have a question, but I was wondering if you think it is possible to get some interesting results for those models as well, or if it's way too complex. And I found it interesting that I think it's really hard to study this case with ODEs, but renewal equations and PDEs may allow to do something.
Certainly, I think it is somehow easier, in a sense, to formulate it in terms of renewal equations, because you have this top-down approach where you, you start by introducing this capital A, which captures everything, but then indeed has the difficulty that you point out, that it contains so much that you have to really look at submodels of how it is composed of, first of all, meeting, so contact intensities, then infectiousness itself. And the combination may be difficult, because if you are maybe very infectious, you're also very sick and you stay at home in bed and you don't go out. So to make it really concrete for a specific disease, you have to work out what this A is and what you put in as further, more, say, lower level modeling ingredients to build up the capital A. I think in many cases it may still make sense to have the separability, in the sense that it depends on X as a factor and on the other two together. But I'm not sure. It depends on the precise interpretation of heterogeneity. It depends on the disease. It depends on what you want to investigate and to model.
Right. So you would say go specific before you want to.
But as you know, I am actually interested in extending pseudospectral approximation to the infinite dimensional case. Right. And it's exactly for this reason that if you have this S of t and x and no special structure in the A, that's the situation that you have. You have a renewal equation for a function of time that takes values in a space of functions of x.
Yeah, no, and indeed, I was thinking that with this susceptibility example, then if a person has is highly susceptible, then the relation. So if the transmission depends also on susceptibility and on infectivity, that really, like, considering a non-separable kernel makes sense.
No, but wait. You have to be very careful. The separability concerns the two individuals. So it may very well be that is, if you have like AX is X and C of psi is psi, you have that there's complete correlation, or actually the activity influences both your susceptibility and your infections. Of one and the same individual, it has an impact on both. The separability concerns the trait of one individual and the trait of the other individual that are into contact. So it is non-assertive in some sense. You don't, the easiest example is, I think in those days of HIV, the idea was these very active, sexually active individuals, they go to bars and they meet at random people that are in the bar, and they don't meet people because the trait is somehow attractive to them. It's just at random in this weighted manner of how often do you go to the bar. Right. That's the kind of situation.
Yeah, thank you. Thank you.
Thank you. I think that now it's Marino's turn.
Hi, Odo.
Hi, Marino. That's a long time.
Yeah, that's a very long time. Well, I have a very interesting talk. I'm not a mathematician, so I got lost in a certain way. But there's one question I want to ask you. Is there a way to include sub-threshold epidemics into the renewable equation paradigm? I mean that you might have an epidemic, even if are not as smaller than one.
There's two ways in which I can imagine this. One is that it's due to the discrete nature of individuals, and so you have like a branching process that may go extinct, but first have like an outbreak that is not negligible. The other situation is due to the heterogeneity. You may have that it's very infectious among a group of people, or let me put it differently, that there's a group of people that meet each other very frequently, and that but it is a smaller group, and so within the group you may have like an outbreak, but it doesn't really get very far out of the group. So if you average, which is what this R naught business does, over a longer period, it may go extinct.
But is there, I mean, can you, because when I have a compartmental model, I know how to derive a sort of indicator on whether you might have or have not a sub-threshold epidemic.
Yes, so you are, when you talk about compartmental models, it means you are in the deterministic situation. So it must be due to this heterogeneity that this is possible.
Yeah, it might have a reactive system. You know, a system that is reactive. Now, is there a way to, in a way, study reactivity?
I'm not sure that I understand what you mean by reactivity, but I would say in general, everything you can do with ODE, you can also do with renewal equations. In the theoretical sense. I mean, the tools and how to make it, how to compute things may be more involved and more difficult, but from the theoretical point of view, there is no obstruction.
Okay, thank you.
But it seems I should read your stuff on this sub-threshold epidemics. I haven't read it, so so if you can send it to me, it would be very nice.
Oh, yes. Okay, I will send that to you.
Okay, great, thanks.
Okay, thank you. Are there any more questions or comments? So it doesn't seem so. I have just one comment or little question about this lack of tools for renewal equations. And I think you mean either analytical or numerical tools.
Right,
I guess. But don't you think that the reason for this is just because, I mean, basic courses are on ODEs. It's very difficult to teach renewal equations at degrees, or is that, or is there something else we can do?
I think it has to do also with the number of users. It's just that ODEs are used in all kinds of areas, in physics, in chemistry, in biology, everywhere. And so the population of users of ODEs is so enormous that it really pays to make tools and make them user-friendly and to develop them, etc. And in contrast, renewal equations, it's a very small community. Now, of course, I hope this will change, but I'm not sure. I think in my opinion, in modeling courses in particular, it would be very nice if more attention was paid to renewal equations, because I still believe that that they are, in essence, very simple. It's just that we are not used to think in those terms and are trained in ODEs and trained in writing down ODE models, that they are not used that much. But there is no real reason that the reason is not that they are more difficult. Really not.
Yeah.
I don't think so.
So less present, maybe.
Yes.
If you have patience, just a short question, last question from the chat from Rinaldo. To which extent can renewal equation be written as partial differential equations?
So very often they are just integrated versions of partial differential equations with non-local boundary conditions, like in the H-dependent situation. But also, if you want, you can write a partial differential equation and integrate it along characteristics and then substitute it into an integral and you get a renewal equation. I think in some way this is not needed. You just can write down the renewal equation right away.
Okay. Thank you very much. So
Dimitri, make an announcement.
Sure.
Finish. Okay. Thanks to everybody. Thanks to Odo very much for the very nice talk. I want to remind you that we will have another seminar in 2 weeks by Jane Heffernan. And also to remind that there will be a course on epidemic models, a CIMA course on Cetraro, where you can listen to Odo for a whole week that will present the material in much more detail. And there will also be other speakers like Tom Britton, Chris Donnelly, and Maurizio Falcone, and other activities. And so if you're interested, please look at the site of the CIMA, and I think that would be an interesting thing about epidemic models. And goodbye to everybody, and see you in a couple of weeks, I hope.
thank you, Odo. Bye-bye, everybody.
Yeah, bye-bye.
Bye-bye.